So now we can do inference. We're going to use the AOV command. Like I said, it's a lot like the LM command, and it also works best if you save the result into a named R object. So I've written a line of code for you here, and you could just run it. You could click the play button or Control Enter. And then I'd like you to see what happens. So nothing prints out in your console because we're assigning the result of this function into the name A1, but something is going to show up in your environment. So now I have something new in the data section of my environment. And just like when I was talking about regression, here I'm using kind of a dumb name. I'm calling my Anova model A1, and then if I made another one, I would call it A2. You could be smarter than me and you could come up with a smarter name than that, but that's the default name that I use. So this did something, but it didn't really give us any useful information. We'd like to run the summary command on that object. So if we do summary of A1, we Control Enter, now we get out the Anova table. So this hopefully looks familiar from lecture. We've got our row, which is about the groups. We've got our row, which is about the errors. And then R doesn't actually give us a row for the total, but we could add things up if we really needed to figure out something about the total, because all of the rows need to add up. So we have 4 degrees of freedom for the groups, which makes sense because we said we had 5 groups. 5 minus 1 is 4. We've got 1, 3, 7, 6 for the error, because that's what residuals are. It's the error. And then we could just add these numbers together. So 4 plus 1, 3, 7, 6, 1, 3, 8, 0, total degrees of freedom, because that needs to add up. And then the next question is, what is our test statistic and what is our p-value? In this case, our test statistic is an f value. So the test statistic is the f value, 2.752. The p-value is 0.0269. And then what is our generic conclusion at the alpha equal 0.05 level? We reject the null hypothesis because 0.027 is less than 0.05. We have evidence to suggest that at least one of the mean number of hours worked is different. So at least one of those categories is different, but we don't know which one. So that's the thing that's kind of frustrating about Anova, is once you reject the null hypothesis, you just know something is different, but you don't know what is different. And then what comes next is inference after Anova. So if we're going to do inference after Anova, we have to have rejected the null hypothesis, which we did, and then we're just going to do inference like on a single mean or a difference of means, basically the same way that we've done in chapter 6, but we're going to use the square root of the mean squared error to estimate the sigma instead of using the sample standard deviation. If we're doing a confidence interval or a hypothesis test for the difference of two means, this is my standard error equation. It's the square root of the mean squared error times 1 over n sub I plus 1 over n sub j. So we're going to think now about the difference between the number of hours worked per week by divorced people and married people. Those look pretty similar to me looking at the boxes, but we're going to use statistics to tell us that. So we might want to estimate our standard error. And so we're going to use our mean squared error, which is from the mean squared column of the R output, and it's the residuals row. So the mean squared error is 208.6. And we could do the square root of 208.6 times, and then we need 1 over ni plus 1 over nj, but we need to know what those ni and nj's are. I think I'm just gonna go back and find my code where we were checking the conditions, and maybe I could paste that in again here. Let's see. So I had 400, nope. Apparently I was using some old numbers here. I've got 239 who are divorced and 618 who were married. Okay, so this would be the square root of the mean squared error times 1 over the sample size for the divorced people plus 1 over the sample size for the married people. And then I could control enter, and then that would tell me my estimate for the standard error is 1.1, basically. That's how we could figure it out. When we're doing inference after ANOVA, we're using a t-distribution, and we're going to use the degrees of freedom from the error. So we're going to use these degrees of freedom. So in this example, the error degrees of freedom are 1,376. And we could write out the math using R as a calculator, like we've done several times in labs, but the easiest way to do pairwise tests in R is to do all of them at once using a particular function. So if you do a lot of tests at once, you could end up in this problem of multiple comparisons where you have done so many tests that you're going to find some that are significant just by chance. And one solution to that problem is to do the Bonferroni correction. With the Bonferroni correction, you just divide your alpha cutoff by the number of tests you're going to run. So if you had alpha equal 0.05 and then you were going to run 10 tests, you would set it down to be a cutoff of 0.005. So that's the kind of easiest way to think about doing that kind of correction. There's other more sophisticated methods, and one of them is called Tukey's honest significant difference, which is a sort of a dig. John Tukey was a statistician, and he was sort of coming back at another statistician who had a different kind of least significant difference, LSD, and so Tukey came up with his HSD. And we're going to use Tukey's HSD just because it's pretty easy to use in R. I'm not going to talk about the details here, but it works a lot like the Bonferroni correction. So we're going to create an 80% confidence interval for the difference between the number of hours worked by divorced and married people. And the way that we're going to do that is we're just going to run TukeyHSD. And you have to be careful about the capitalization. It's capital T and capital HSD, but then the rest of it is lowercase. And then you give it the name of your ANOVA model, and then you can tell it the confidence level you want. So if I run this, I'll control enter. This gives me a bunch of information about all of the different possible pairwise differences. So married and divorced, never married and divorced, separated, divorced, etc. So which pair did I say we were interested in? Divorced and married people. So let's see, we had married and divorced. That was this first row in our output. And then we could interpret the interval. So I am 80% confident that the true difference in mean working hours between married and divorced people is between negative 2.92 hours and 1.80 hours. So I'm looking at the lower end of the interval and the upper end of the interval, and that interval contains 0, so we really aren't sure if there's a difference in the average working hours. Okay, so with married and divorced, it kind of looked that way on the plot that there wasn't a difference, and we just confirmed that. We're really not sure, even at the 80% level, if there's anything going on there. We could also think about hypothesis tests. So the output gives you the difference for each one of these pairs. It gives you the confidence interval at whatever confidence level you specified, in this case 80%. And then it also gives you a p-value. It's an adjusted p-value. And again, I'm not going to get into the details of how the adjustment is done, but you can just use it like a regular p-value. So small p-values mean something is significant, large p-values mean something is not significant. So if we think about the hypothesis tests and the ones that showed significance, it is the difference between widowed and divorced. Maybe I'll just copy this. Widowed and divorced, widowed and married, and widowed and never married, and widowed and separated. Those are the smallest ones. And actually, I think widowed and never married, that's actually greater than 0.05. So let's take that one off. So those are the 3 significant differences, right? These are all less than 0.05. Yeah. So just 3, widowed, divorced, widowed, married, widowed, separated. Those are the only ones with p-values less than 0.05. So this has already been adjusted. We don't have to worry about additional family-wise error rates. That's been fixed for us. So those are the only 3 significant differences. Widowed is different than divorced, widowed is different than married, and widowed is different than separated. But there's actually maybe not a significant difference between never married and widowed. And all the rest of them, no significant difference in between them. So that's what ANOVA lets you do. It lets you see if there's a significant difference between the means, and then you can do inference after ANOVA to tell you which of the means are significant.